Understanding how the world works with precision, being able to predict how certain physical systems will respond to changes quickly is really one of the key skills when you're learning physics. And so we're going to see our first mathematical relationship today called the direct proportion that we'll see all year long in many different physical phenomenon. And the key takeaway for you today is going to be this new way of looking at a math equation. In the same way, if you just look at my intro picture here, I'm showing you a circle rolls and a square does not. You know that immediately. It's automatic. You don't have to think about it because you have this deep understanding of how physical concrete objects in the world move every day from your experience. And in the same way, we want to turn mathematical equations into that same automatic process. So when you look at an equation in physics, you'll be able to know exactly how that system will behave. More specifically, how will certain variables respond to changes in other variables. And that in doing so, and being able to do so quickly without getting bogged down in a bunch of minutia of calculation, will really open up your thinking in physics and allow you to solve much more challenging problems than you thought possible. So that's what we're going to work on today, is learning about this first relationship called the direct proportion. So here we have a very simple function, y is equal to 3x. This is an example of what is called the direct proportion. And what I'd like to do first is locate some places in all of these data tables where we have x changing by a certain factor. So for example, I'll do the first one here, and let's change x by a factor of 2, meaning let's double the value of x. Where can we see a doubling in x? Well, for example, we could start with a value of 2 and then multiply that by 2, which is a doubling. So we're starting if x is equal to 2. I'm just arbitrarily picking that one. We're doubling x, so 2 times 2, that gives us 4. I'd like you in the next data table to the right to find another place in the x column here where you can double x and follow this notation. Or we start at a value you want to begin at, anyone's fine, as long as it will be able to be doubled in our table. Our table only goes up to 9 here. So find another doubling. Pause the video and try that. All right, pretty easy. I'm going to just choose this one that I found. So I'll start at the number 3. And to double 3 means to go to the number 6. So there's another multiply by 2. So this is just a simple shorthand notation I like to use showing these factors of change in a variable. Okay, now let's correspondingly see how y responds. So we have this model, this equation up here, y is equal to 3x, and we've written out all these values, x's and then the corresponding y's. And we want to see how does y respond to this doubling in x. So try that in both cases, and all you need to do is draw some arrows and see if you can figure out how y responds and by what factor y changes when we double x. So start with this one and then take a look at the next one over here to the right. Go ahead. So I've drawn in the arrows on both tables that correspond to the arrows for the x column. And if we just now look at the numbers, we can see y has gone from the value 6 to the value 12. And what is that in terms of a factor of change? Well, that's a factor of 2. So we'll write that in times 2. And then let's see what happens in the other table. Well, here we began with a value of 9 in y, and we go down this arrow corresponding to this row here where x is 6, and now we see y is 18. What factor of change is that to go from 9 to 18? Well, that's multiplying y by a factor of 2 as well, a doubling. So we'll write that in here. So right off the bat, I hope you can see what's happening here. Apparently, it looks like when we double x, no matter what x starts out as, doubles. So that's validated here in the first table, same here. When x doubles, 3 times 2 is 6, y also doubles. Let's try that one more time and see if our test continues to hold true, find one more doubling in this third table and see if y also still doubles. Hopefully this makes sense and is easy for you, but I really want you to see this key point by looking at these data tables. So pause and try that. All right, so we see another doubling in x as we go from the value 4 to 8, and a corresponding doubling in y as we go from the value 12 to 24. So we can now generalize this property based on these tests. I mean, we could keep going if we wanted to, and I invite you to perhaps do that, but it is shown to be true now that when x changes by a factor of 2, y changes by a factor of 2 as well. That's cool. So we've changed x by some factor, and it looks like y is responding by changing by the exact same factor. I wonder if this property holds true for other factors. Maybe we could try to triple x, or maybe quadruple x, or 5 times x, etc. Well, why don't we try that? Why don't you use these last two tables over here to try and triple x twice. So do a tripling here and then another tripling here and see how y responds. And then we'll generalize some more properties about this. Go ahead, pause and try that. All right, so I've picked out a couple places here. You can see if x goes from 2 all the way to 6, that's a tripling. And likewise, y goes from 6 all the way to 18, which is also a tripling. Another place where a tripling occurs is to go from the x value of 3 all the way to 9. So that's 3 times 3 is 9, and then we get 9 going all the way to 27, so 9 times 3 is 27 in y. So it looks like when x changes by a factor of 3, in these two examples here, y changes by a factor of 3 as well. Now we could try this by doing a factor of 4 and a factor of 5, a factor of 10, a factor of a million. It doesn't matter. And what we're going to find is when x changes by some factor, whatever factor that is, y changes by the exact same factor. This is an amazing property of this type of relationship that we call the direct proportion. Now this insight is going to lead to your ability to think very quickly about systems and how they will respond to changes. And we'll look at that at the very end of this video when we kind of turn this into a more realistic example in terms of the physical world. Right now we're just still in kind of math variables, x and y. But I want to build up a more abstract notation to talk about these factors of change that I like to do. If you noticed before, we were using data tables and looking at all these particular values, and that's tedious, but we need to do that when we're first kind of building up this intuition. So to kind of take us to this next level of abstraction where we can start to just see things symbolically and communicate things symbolically, let's just start out still in this land of choosing specific numbers. So to take a look, here's x over here, oops, and we're going to increase x by some factor. I hope you can see by what factor we're increasing x by. It's by a factor of 4, so 2 times 4 is 8. And then obviously y is going to respond in exactly the same way. So in this function, we would be starting out as y is equal to 6 when x is 2, and then y is going to change by the exact same factor of 4. We don't even have to think about it. We don't even have to go to the equation and plug in now for our new x value. We don't have to do that at all. All we have to know is that x increased by a factor of 4. It changed by a factor of 4. Therefore, y must do exactly the same thing because this is the direct proportion. So we can just put a multiply by 4 here. And that'll get us from 6 up to 6 times 4 is 24. So we'll put that in here. Great. So again, those are just using specific examples with numbers, test values, if you will. Now, I like to consolidate this type of notation into something a little bit more compact that looks like this. And I want to see if you can figure out what I'm doing here. So let's do this. I'll just write it out, and I'll pause the video and see if you can like think about what I'm trying to communicate now. All right. So I'll just say over here, just more abstractly, colon. All right, here we go. So I'm going to go x and then this little arrow and then the number 4x and then y in this little arrow. And then I'll just put that there for now and then y like this. Okay, pause the video and see if you can understand what I am trying to communicate on the page here in this notation that I like to use. Okay, go ahead. All right, so let's explain it. What I'm trying to say in the simple notation is that x is going to change. That's what this arrow is. X is going to change by a factor of 4, or 4 multiplied by x. This is multiplicative thinking. X changes by a factor of 4. It goes from x to 4 times x. And then, as we have learned here today with the direct proportion, y is going to respond to that change in x by also changing by a factor of 4. So y changes by a factor of 4, or y goes to 4 times whatever y originally was. Now, this notation is simplified because it's not having to use specific values. But just watch out, because it's implied here that we're going to obviously a new value of x when we go to the right, but we're still using the same symbol x here instead of like x initial and x final. Sometimes people do that, but I like to do it in this way where you just say x is going to now 4 times as much x. All right, so a simple notation there for communicating these factors of change. All right, now another little question that's important to notice is, what if we change something about this number that is in front of the variable x in the equation? So before it was y is equal to 3x. Now I've changed this value to 7. And this value is the constant that's out in front of the variable x. Since we're just using general math variables, we don't have any units here, but we'll see in physics, of course, units are important. But prove it to yourself that this property still holds, even if we change the constant value. So when x goes to 4 times x, y will still go to 4 times as much y was before. Try to pick out some test values and prove that is indeed true. Pause the video and try that. All right, so I just chose some values. So 2 and then quadrupling x to 8. And we see a likewise quadrupling in y. We go from the value 14 all the way up to 56, which is a multiplying also by 4. So what we've just proven here, and you can do this with other values if you want as well, is that this constant out in front does not matter at all for this property. That's nice, because we don't have to really get bogged down in really thinking about this constant when we're trying to reason about how y will change when we change x in a certain way. We can effectively just ignore this constant or any other constant. For example, I could come up with a function that looks kind of weird, something maybe like this. Let me write it out here in the same color. What if we had something like y is equal to, I don't know, I'm going to do 2 times 3 divided by 5. And that's just some crazy looking constant, which you would never write like that in a math equation with numbers. But just imagine that, this 2 is some separate value, and 3 is a separate value, and 5 is a separate value. But these values are never going to change. They're always just some constants always out in front here, right? Well, likewise, we could effectively ignore this. If you just kind of worked all the math out, this would be 6 over 5, and that number would never change here. It's just a constant, and we'd be fine. Now, oftentimes in physics formulas, we'll find that not only will there be numbers that will be constants, but there will be other variables as well that will never change. Those will be constants. And we can effectively ignore those as well. So you could come along and maybe write the same formula here I'm writing, something like this. I'm just going to make up some constants, maybe like a times b divided by g or something like that, and then multiplied by x, where every single one of these things, a, g, and b, those are all constants that will never change their values no matter what. And likewise, because of that, just as we reasoned, we went from y equals 3x to y equals 7x here, and we noticed that this property of factoring changing didn't change in any way. We still had this property when you quadruple x, y quadruples, when you triple x, y triples, etc., etc. Same thing here. We can effectively ignore all of these constants in our analysis, and we'll still know, no matter what these values are, even if they're not specified, these constant values, if we double x, then y will also double. So I'll write that out again. If, and I'll write this up here, we 100x, then y will also change by a factor of 100 as well. And it absolutely does not matter what these constants are here. Now, because of this, there's a way we can now extract out of what looks to be a complex formula. If you look at this, it looks kind of complicated visually, right? But really the only important thing is how y and x are behaving together, right? We don't really care about this constant here when we're looking more abstractly at the formula. So we can extract out of this formula what's called the mathematical relationship and then write that down. So let's do that now. So I've written out all four of those functions that we have just been talking about, and they all behave the same way. They just have different constants out in front, so you'd get different particular values for x and y. But if we just kind of visually look at this and put a box around everything that's a constant, you should be able to see now that it's the same type of relationship. We've got y here and x there, y there and x there, y there and x there, and then y here and x here. This is the direct proportion. So we now extract out of that the relationship by writing it in this following way. You might have seen this before, but here's how we do this. We say that y is proportional to x. That's what this little symbol is here. It's called the proportional to. Proportional to. And it's not an equal sign, so this is no longer a formula here that you could plug any numbers into. Instead, it's just a more general abstract way to represent the fundamental relationship that all four of these formulas have identically. Y is proportional to x. And this is what we call the direct proportion, and it has this property. So right here, this is how we state the relationship. Okay, I'll just actually write that out here. So this is the relationship. Y is proportional to x. It's called the direct proportion. And it has this property, and I'll write that over here. Let me try to move this down a little bit, actually. Get this whole thing down. And we'll write property. So it has this property whereby when you change x by some factor, y will change by the same factor. So we could write that in a couple ways. We could do when x goes to 2x, y will go to 2 times as much. We could write it again. When x goes to 3x, y goes to also 3y. Or we could write it more generally, which might look a little weird and abstract, but you could say when x goes to some factor n times x, then y will also go to that factor n times y. Okay. So this is now the property that we've discovered, and we discovered it by just looking at all the numbers in those data tables. And now we're trying to represent all of this abstractly. All right, let's finish this video by just bringing this now into the physical world, still with some abstraction, but I want to get you a sense of how in physics we can construct equations that represent the world with all these different variables, and being able to distinguish between what are the constants and then what are the variables in the mathematical relationship. So here I have some formula. Z is equal to the square root of 3 times g divided by b cubed, and then that multiplied by h. Okay. Now g and b are constants of nature. They'll never change. The number 3 is a constant as well. And if this was an actual formula, we'd probably have to have units on this number 3. I'll just leave that off for right now. And what you should see if you were to extract now the mathematical relationship like we have just done is that this whole thing is just a constant, and the relationship between z and h is the direct proportion. So we would come along and realize that z is proportional to h. This is the direct proportion. Therefore, if we were to change h by some factor, in this case, I'm changing it by a factor of 5 arbitrarily, and maybe in the physical world, this h represents a certain height above a ground level here, right? So we could say, well, we start here with a ball. It's a certain height h above the ground. I'm not even specifying the number of meters it is above the ground. I don't even care. I'm just saying it's some initial value h above, and then I'm going to change that physical scenario somehow, and I want to know how this other parameter z will respond to that change. So I will come along and I will multiply by 5 the height. And now without plugging in, without getting bogged down in this square root and all these constants and whatever visual complexity you see here, because I can extract the relationship and I know the general property of this relationship, I can immediately see how nature will respond. I know immediately that multiplying h times 5, going up to 5 times as much height, will produce 5 times as much z, whatever z represents in the physical world. I'll say that explicitly here. As h goes to 5h, or 5 times the height, z will now go to 5 times z, whatever that is. Maybe you can make some things up for it in your own mind. Maybe it could be time. That's actually not how time works with height, but it could be some physical parameter about this system that is of importance, and we immediately know it now, almost instantly. I mean, when you get the hang of this, you can look at this formula and you can extract the relationship in like 3 seconds, and you can go boom. If I 5 times the height, I'm going to 5 times z, whatever z is. Okay, this is very powerful thinking, and it's taking you from this plugging into equations and starting to see instead how these equations tell a certain story about a system, and how you can see that story very quickly when you can think more abstractly like this. In the exact same way that you can know that a circle will roll when you see it versus a square will not roll. You don't have to think about it, you just know it, and now we want to build up this property by looking at equations. All right, so there we have it. A little bit long on the video, but I wanted to go through all of this specifically and start to build up this intuition about mathematical relationships, and we'll be seeing more. This is our first one called the direct proportion. There are others as well. All right, so take care. We'll see you in the next video.